In today's lecture, we are going to talk about Newton's law of viscosity. Up till now, we have talked about different strain rates. We have talked about volumetric strain rates. We have talked about shear strain rates using material line. And now we are going to take this a step further and talk about how stresses could be related to strains. Now, this is something which is known as the constitutive behavior of fluids. By constitutive behavior, we mean that what would be the physical behavior of a material, in this case a fluid, if it comes under specific conditions. So here we are talking about constitutive behavior of fluid. The physical behavior which we are looking into would be the change in strains, and the specific condition to which that fluid is in which the fluid is kept would be the condition of stress. So we want to see that how stresses are related to strain rates. In that, we are going to talk about Newtonian fluids. Now, Newtonian fluids are those kinds of fluids where stresses are proportional to strain rates. These are Newtonian fluids. Now, for these type of fluids, we can say that tau, which is our stress, is directly proportional to strain rate. Now, keep in mind, we are not talking about strain only, we are talking about strain rate. That's why gamma dot. Gamma here is my strain. Obviously, I'm talking about shear strain here, and gamma dot is shear strain rate. Using mu as my coefficient of proportionality, I can say that my shear stress is equal to mu times gamma dot, that is my shear strain rate, where mu is coefficient of viscosity, and I can say this coefficient of viscosity is a property of fluid through which it resists strain. Many commonly occurring fluids are Newtonian in character, for example air, water, etc. And when I say that they are Newtonian in character, by that I mean that tau is directly proportional to gamma dot, that is shear strain rate. Now, viscosity is a physical action which happens due to resistance, when there is a resistance to strain through molecular forces. Now, in order to understand the effect of viscosity, let us take a thought experiment. Okay, let's look at a thought experiment. In order to understand the effect of viscosity, consider a simple shear flow having a velocity distribution, a three-dimensional velocity distribution, such that the x component u velocity is dependent on y and 0 v and w components. So let's look at it here. I have my coordinate axis, x direction and y direction. Along x direction I am having flow. It's a unidirectional flow. From bottom, this is the bottom part where my velocity would be 0, and then it would go on increasing. Okay. Now let's look at a plane at y equals to y0. So fluid particles moving immediately above the plane y equal to y0 are moving faster than the fluid particles immediately below the plane y equal to y0. By that we mean that if this is my y equal to y0, then fluid particles here would be moving faster as compared to the fluid particles here. That's what this means. Okay. And this happens because of viscosity. Now, generally, experiments are performed to find this relationship, this constitutional relationship. That is, how are my stresses related with my strain rates? Now, let's say for a Newtonian fluid, we would do a similar experiment by changing strain rates and drawing a curve between stress and strain rate. And let's say I get this kind of curve over here. This slope is nothing but tan phi, and this is actually characteristic of a particular fluid at a particular pressure and temperature. Meaning by, if I keep my pressure and temperature same but I change fluids, then there is a possibility that this slope would change. I can also say that for a same fluid, if I would change my pressure and temperature, then again there is a possibility that this slope would change. From this curve, I can find the relation and I can say that tau is equal to tan phi times mu dot. This is for Newtonian fluids, where this tan phi is nothing but coefficient of viscosity. Now this is something for Newtonian fluids. There are other constitutional relations also. Okay. So let's say in general, if I would look at a relationship between stress and strain rate, then I can have something like this. Either I can have a straight line, that is for Newtonian fluids, where I would say that my n is equal to 1, where a general relationship between stress and strain would be something like this: stress and strain rate, that tau would be equal to k times, it's a coefficient of viscosity, gamma dot to the power n. Now this n could be equal to 1, and that would make it equal to, that would be the case for Newtonian fluids. This n could be less than 1, denoted by the red curve here, or it could be greater than 1, shown by the blue curve. For n greater to 1, my viscosity decreases with the increasing strain rate, and for n less than 1, my coefficient of viscosity, it actually increases when I am increasing my strain rate. Okay, so this is would be the case. N less than 1 and n greater than 1 would be the cases for non-Newtonian fluid. Okay, these are the cases for non-Newtonian fluid, and this is the power law for fluids. And I can say that my coefficient of viscosity is nothing but d tau by d mu dot. Okay, and from there I got this relation that my applicable is n k times gamma dot n minus 1. If you want, you can go to your book, either F.M. White, or you can go to Fox McDonald and read more about it, and you can get more details from the book. And I would recommend that if you go to the book F.M. White, they have a very good description of viscosity, and if you would look at your syllabus, then Newton's law of viscosity comes in unit 1, but I like to cover it with unit 2, because then you have already gone through different type of strains and how through kinematics you can get those strains. That's why this portion was not covered in unit 1, and now it is covered in unit 2. Now, like we talked before, this coefficient of viscosity, it is a function of temperature and pressure for Newtonian fluids, definitely I'm talking about. Now, it is a very strong function of dependence of coefficient of viscosity is strong on temperature, meaning by if I change temperature, then the viscosity changes more quickly as compared to the change in pressure. So if I change in pressure, if I make a change in pressure, then the change in viscosity would be less as compared to this same amount of change in temperature. So let's say for a unit change in temperature, the change in viscosity would be more as compared to a unit change in pressure. There is another phenomena which you might have already read, that the coefficient of viscosity for a gas, it increases with increase in temperature, but the viscosity or the coefficient of viscosity of a liquid, it decreases with increase in temperature. Now, to understand this, why it happens, we need to look into what causes viscosity. What are the reasons for viscosity? There are two predominant reasons for viscosity. One is the intermolecular forces of cohesion, and second is molecular momentum exchange. Now, for the case of gases, the molecular momentum exchange is the predominant reason for viscosity. So when we increase temperature, this molecular momentum exchange increases, and that is something which increases the viscosity for gas. In case of liquids, it is the intermolecular forces of cohesion which is the main reason for the presence of viscosity. And for the cases of liquids, when we increase this temperature, the intermolecular forces of cohesion decreases, and that is the reason we see a decrease in viscosity with increase in temperature. Okay. Now, after covering this, the next portion to which I would like to progress to would be the flow kinematics near a solid fluid boundary. And this is something of great interest to us in engineering applications also. So think of a solid surface, okay? It's a boundary. On one side we have fluid and the other side we have solid. Take a point A on this boundary. Now, tangential to it, I have a unit vector t hat. Normal to this point on the surface is n hat. Okay. Now, because of viscosity, I have a no slip condition, and no slip condition is nothing but in the tangential direction, the velocity of fluid Vf would be the same as the velocity of solid. This is known as the no slip condition, and it is one of the most important conditions once we are considering solid fluid interfaces. Okay, so Vf, which is the velocity of fluid, dot t, this means that the component of velocity of fluid along the tangential direction at the boundary would be equal to Vs velocity of solid dot t, and it means simply that at the interface, at the boundary, solid liquid, solid fluid boundary, the velocity of fluid and the solid would be the same. The second condition is known as no penetration condition. For most of the cases where the solid surface does not have any pores or holes, for those cases this no penetration condition holds, and what it means is that the velocity of fluid perpendicular to the surface is same as the velocity of the solid. So at point A, the velocity of fluid perpendicular to the surface would be the same as the velocity of the solid perpendicular to the surface, and this is known as no penetration condition. So these are the two kinematic conditions which are considered, boundary conditions which are considered at solid fluid interface. Definitely if there are pores or holes, then the second condition would not hold exactly like that, and there would be slight changes to it. Now let's talk about the application of Newton's law of viscosity. uh, whenever we have flow between two similar surfaces which are separated by a narrow gap. So I have taken two examples here. These are two surfaces separated by a narrow gap, okay, and in between we have fluid. I have shown my coordinate axis as here, x in the direction of flow, y perpendicular to it. Now this bottom plate is, let's say, at u equal to 0, and the top plate, which is at a height h, it is equal to u1. So the velocity profile can be shown something like this. So here I am showing that u is a function of y. U is a function of y, that my velocity is changing when I am moving in y direction. Another approximation at this stage which I have taken is that changes with respect to y are much greater than del u by del x or del u by del z. So this is one case. The other could be when I am having rotational motion, that I have a solid surface, then I have another solid surface on top of it, and it is moving at omega. The gap between these two solid surfaces is h, and the top surface has a radius of r, and this holds good when I am talking about h by r much less than 1, which means that my h is much smaller than my r dimension. Okay. Now from before we know that my shear strain rate is actually del u by del y plus del v by del x, and from that I can say that my shear stress, which is equal to viscosity times my shear strain rate, would be tau, would be equal to mu, and then this is gamma dot xy. Okay. Now the flow in the small gap separating the two surfaces may be induced by imparting tangential motion to one of the surfaces relative to the other. You just need to give a tangential motion to one of the surface relative to the other. Now because the gap is very small, the tangential velocity imparted to the fluid as a result of no slip condition has the largest gradient in the direction normal to the surface than in other two directions. So this is the same thing. So del u by del y is much larger than del u by del x or del u by del z. That's what I'm saying here. Okay. That the tangential velocity imparted to the fluid as a result of no slip condition has the largest gradient in the direction normal to the surface than in other two directions inside the narrow gap. Thus, the velocity variation only in the normal direction may be considered to be significant. So, in this particular case, instead of taking both of these terms, since del v by del x is very small when compared to del u by del y, so I can say that my shear stress is equal to mu times del u by del y, and that is the reason I would neglect my del v by del x or del v by del y, and I would only consider simply tau is equal to mu del u by del y. Okay. Now if I want to find the force, I can find the force. I simply need to take my shear stress, multiply it with the area, and I can get my force. If I want to find the moment created, then that can also be found. I simply need to multiply it, take a cross product with the distance. Okay, so that's all I need to do. Okay, so that's pretty much it. And let's say this was for a single degree of freedom, but let's say there are forces, let's say there are motion in both the direction. So a general case would be for a shear strain rate del u by del y plus del v by del x, if both the terms are comparable to each other, then we need to take both of them, or if any one of them is predominant, then we just need to see that we would take one of them and drop the other. So just to let you know that whenever you see that tau is equal to mu del u by del y, this is the case when you are neglecting del v by del x. You are neglecting del v by del x because del u by del y is much greater than del v by del x. Okay. Otherwise, this actually del u by del y actually is a part of shear strain rate, and complete shear strain rate is del u by del y plus del v by del x. And the only reason that you are only looking at del u by del y is that the other component is quite small. Now that finishes our Newton's law of viscosity. I would recommend that you look at sample problems from both F.M. White and Fox books. That would give you a good practice, and after that you can go to unsolved problems and tackle them. Thanks.